So today we're going to look at exponential growth and decay. There is a general formula that we are going to apply, and it looks like this. And our k is going to be greater than 0. So n equals n sub 0 e raised to the kt. Let's take a look at what each of those pieces mean, because we're talking about exponential growth or decay, and we're basically talking about populations. So this one is going to be our final population. After a certain amount of time, so after t. When it's n sub 0, that sub 0 means initial. So this whole point is the initial population. Remember, e is just a constant. K is also going to be a constant for that particular equation, depending upon the situation that's been set. So this is going to be a constant. And that constant is considered to be our growth rate. And then our t is our time. And our t is going to be measured, depends upon what the situation calls for our population. So we're going to use all this. Notice it looks a lot like our formula for growing that we used yesterday. The ending, the beginning, our constant, our rate, and our time. It's the same formula. We just change the letters to indicate that it is a different situation. So we're going to take a look at some examples. So our example is going to be about a fox population. It says that it has a relative growth rate of 8% per year. In the year 2000, the population was 18,000. So we want to know what the population was in 2006 for the first part of this question. 8%, well, let's take a look at what pieces we know. The growth rate right here of 8%, this is going to be our k. And just like when we were using the interest formula, the percent of growth is going to be measured in decimals. So 0.08 is our k. In the year 2000, so this is our beginning year, that's going to help us in finding this one. Population was 18,000, so our initial population is 18,000. So we know k, and we know our initial one, and we're trying to find one of the others. In this case, we're looking for what is n, the population in 2006. So it will be 18,000, our initial population, times e raised to k, which is 0.08, times, and our t is going to be not 2006, because we want the growth from this year to this year. So from 2006 to 2000, or from 2000 to 2006, we have 6 years. So that's what we're going to put in for t. And that's a real easy one. Once we have the formula set up, it'll be easy to do. You just put it in your calculator, 18,000 e raised to, and if you need to make sure that you put this in parentheses, do so, because we don't want it just raised to the 0.8 and not the 6. So you type that into your calculator, and we're going to round this to the nearest whole fox, because we don't want any partial foxes running around our woods. And that comes out to be 29,089 fox. Make sure you put a label on there too, so that we know that we're talking about the same thing. Now, that one's the easiest form of these to do. The next one is a little bit more difficult because I know my ending population. I want to know what t is. So I'm going to give myself a little bit more space on this board. When the population will double, this is going to be the ending. So I'm going to set this up as 2,500 is equal to, and I still have the same initial population, times e, and I still have the growth rate being the same, and I'm multiplying this by t. Now I'm going to solve for t. That's a little bit more difficult, but you're going to do a lot of these, so pay attention because they're going to start to feel a lot the same. The first thing I want to get rid of this coefficient, I'm going to divide by 1,800. That cancels. I'm going to just cancel these out so I don't have to carry the same numbers, around, but I'm going to keep it as a fraction, keep it nice and neat. So I have 25 over 18 is equal to e raised to 0.08 t. I can rewrite this by taking the natural log of both sides of the equation. And the reason I chose natural log is because of this e. When I have natural log of e raised to an exponent, it's going to equal just that exponent. So I will have the natural log of 25 over 18 is equal to 0.08 t. Now it's not so hard to get t by itself. I just divide by 0.08. And then I'm going to put that in my calculator. Make sure I put this in parentheses because I want it of both of those things. So the natural log of 25 divided by 18, and my parentheses, and then divide by 0.08. And the time gives me 4.1 something. It's not the year 24, right? We're measuring from 2000. It's 4 more years. So the year will be 2004. We had a final question here of when does the population double? Double of 18,000 is 36,000. So that's going to be my final population, and I can set that out the same way. I'm still looking for t, just like in part B. So I'll divide by 18,000. Now this cancels to 2 over 1 because it's doubled. Once again, I'll take the natural log of each side. And the natural log of e raised to an exponent is just that exponent, so I have natural log of 2 is equal to 0.08 t, and divide by that 0.08, and I'll get t is equal to 9. That's not the year though. Remember, we add that to the year 2000, our beginning year. So it's going to be the year 2009, the population will have doubled. Yes, this is the same formula, only this time our k is less than 0. The one previously was a growth. Now we're going to look at decay. And an example is going to be like things like radioactive materials that have half-lives. But once again, this is our our final population. This one is our initial. Well, now k is a negative number, so it's our decay rate. And t is still our time. So the example we have is half-life. We're going to do a lot with half-lives. That radioactive material is measured in that. So the half-life of radius-221 is 30 seconds. And I want to know how long will it take for 20% to decay. It doesn't give me a full amount, it just gives me a percent. But my initial amount, if I'm measuring in percent, is always 100%, or 1. My ending amount is going to be 20%, so it's going to be 0.2. I know the decay rate. I do not know the decay rate. I'm going to have to find that, and I'm also looking for t. So I'm not going to use this one in order to find k. I have to do this kind of in a two-step thing. My time is 30 seconds when I can get to half, which is 0.5. So let's first find k using this information. So we're going to use 0.5 is equal to 1 times e raised to the k times 30, and our time is measured in seconds. If I divide by 1, I get the same thing. So then I'm going to take the natural log of each side. The natural log of 0.5 is equal to the natural log of e raised to the k times 30. And so then I'll have the natural log of 0.5 is equal to k times 30. Let's divide by 30. And this is what k equals. I'm not going to give it a decimal at this point. I'm going to carry that into my next part of the problem, because I didn't want to know what the constant of the rate of the decay was. I want to know what's the time to get to 20%. So now my final population will be 0.2. And its still initial population is 1 times e raised to, I'm going to put this whole thing in, the natural log of 0.5 divided by 30 times t, because t is what I'm trying to find. So if I take the natural log of both sides, which is 0.2, now remember the natural log of e raised to anything is just going to be that. So I'll have the natural log of 0.2 is equal to the natural log of 0.5 divided by 30 times t. T is being multiplied by a fraction. In order to clear that fraction and isolate t all by itself, I'm going to multiply by the reciprocal of that fraction. So I'm going to multiply, and I'm going to do it to both sides. So I'm going to multiply by 30 over the natural log of 0.5. Because these will cancel, and leave t all by itself. So this, that's a times, 30 times natural log of 0.2 divided by the natural log of 0.5. Round it to 1 decimal place. You're going to type this into your calculator. Remember, our time is being measured in seconds, and we want the unit on it. You get 9.7 seconds. So we've looked at the general formulas for both growth and decay. There's two particular growth and decay formulas, shortcuts. We look so often for a double or a half that we've created shortcut formulas for them. Now the other formulas will always work if you don't remember the shortcut formula, but here they are. The shortcut formula for doubling formula is a equals a sub 0 times 2 raised to t over d. So this one, the a all by itself, is our ending amount. And our a sub 0 is our initial amount. And our 2, that refers to the doubling in the population. T is going to be our time. And the D, instead of a growth rate, it is a doubling rate. How long does it take to get to double? And it's also measured in time rather than percent. So let's take a look at an example. So here's our example. We're talking about bacteria. They grow very quickly. So a bacteria culture doubles every 0.25 hours, so 15 minutes. But we're going to do it in decimals because we're measuring in hours. At 1.25 hours, there are 40,000 bacteria present. How many were present initially? So what we're looking for is a sub 0. Let's see what we do know. We know that our ending amount is going to be 40,000. We know that our doubling rate was measured in time is going to be 0.25. Our time elapsed is going to be 1.25. So we can set the formula up as 40,000 equals a sub 0 times 2 raised to the time, which is 1.25, divided by 0.25, our doubling rate. Now 1.25 divided by 0.25, I can simplify it, comes out to a real simple number of 5. So I'm going to have 40,000 equals a sub 0 times 2 to the 5th. 2 to the 5th is 32. So I'm going to divide each side of these by 32. If you don't want to do that, you can still keep it as 2 to the 5th. And so then my initial population is 40,000 divided by 32, which will give me 1,250 bacteria. Just like there was a doubling formula, there's a half-life formula. This is a shortcut for our decay formulas because we're so often using half-life, particularly with radioactive substances. So the formula states a equals a sub 0 times 1/2 raised to the t over 8. It's identical to the doubling formula. Instead of what do I want when it's doubled, I want when it's half. So a is my ending. A sub 0 is my beginning. So I'm looking for half-life, and this is my elapsed time, and this is my halving rate measured in time. And we'll do an example with that one as well. So our shortcut formula for decay is the half-life formula, and now we have a sodium isotope, and Na, which is sodium 24, has the half-life of 15 hours, which means every 15 hours the amount that I started with is going to be in half. Determine the amount that remains from a 4-gram sample after 45 hours, and then again after 5 days. Now, in 15 hours, I'll only have 2 grams, but I'm not going 15, I'm going 45 hours. So I'm going to use this formula. I want to know the end. That's what they're asking. And so I'm just going to go A equals, and our beginning is 4 grams. And I'm multiplying that by 1/2, and our time is going to be 45 hours. We're dividing that by the halving, which is 15 hours. So this will be 3, so 1/2 to the third. You can put that into your calculator. And our ending one will be 0.5 grams in just 45 hours. Then we have our question about 5 days. Our halving is in hours. We have to have our days in hours as well. So 5 days is equal to 5 times 24, and that will be hours. So 5 times 24 is 120. So our T will be 120. So otherwise the formula is the same. So 4 times 1/2 over 120 divided by 15. That's not 4.5, it's 4 times 1/2. You're going to put that in your calculator. It's a very small number, so let's expand the decimals that we're going to come out to. Instead of 1, this was just a nice round one. Let's go to 1, 2, 3, let's go to 6, because that's what I have on my answer sheet. 0.015625 grams is our answer. Very, very small amount after 5 days.